Okay, let's start. So, good afternoon, everyone. Okay, welcome back to Plan 252. Okay, so this is the agenda for today. So you have done the quiz, right? And we will discuss about three things. Yeah? So basic modelings and basically this is the introduction of urban transfer planning. So today we will discuss one of the model, which is regression. Okay, maybe many of you are familiar with this. And then we will also discuss the very important model for our traffic, which is called fundamental traffic flow. Because from here, we will discuss about how we will relate between congestion with travel costs, or travel time. Okay. Okay, so let's start. Wait, I will stop with screen 2. So this is, can you see my slide? No problem. Okay, so good. Let me put this here. See. Okay. So we will start with very fundamental of what is modeling. Okay. So what is model, and then how we create the model. Okay. And how the model usefulness, and then talking about a little bit about simulation and Gaussian in modeling. Okay. So this is what I'm thinking. So we are what we model in our own mind. Okay. So everything that we can think of, okay, every story that we heard, okay, or we can think of is actually a mental model. Every concept is basically a model. So when we say about model, okay, this is very general. Okay, so when a model is accepted as a standard agreement by many people, okay, then it becomes reality. Okay, and then it can be implemented into physical things. So you said about tradition, about culture. Okay, this is actually a mental model. At one time in the past, it used to be a mental model of some people, and then implemented, become a standard agreement for many people. The same thing with what we say as moral, nation, money, marriage, education, religion, law, philosophy, even science, mathematics. Okay. All of these are concepts, that when it become a standard agreement, then it become reality. Okay. So my point is, when we said about model, okay, think about something that much bigger than just mathematics. Okay. So in the past, okay, many people try to model the world, okay, using this kind of elements. Okay. So they try to create any kind of thinking, okay, whether it is correct or not, it doesn't really matter, isn't it? So including horoscope is also model, yeah, okay, zodiac and so on. So one thing that important when you learn about modeling is actually talking about invariance. Yeah? So if you understand the meaning of constant, okay, so if you understand the constant, then you understand the actual meaning of the model. Okay, something that fixed, something that is constant. That is the one that you need to think. Okay, it's not the mathematics, it's not the model itself. Something that actually passed between the model. Okay. Uh, After this, I will show you. Then you will see more clearly after this. Yeah. So uh, let's talk about what is modeling. So modeling, what we talk here is not the form of, model of the clay or modeling uh, to display as fashion show. Okay, this is also kind of modeling, but we discuss about process of creating an abstract conceptual model using the object creation. So the purpose is to predict and to control. Okay, so this is scientific modeling. Yeah, that can include miniature model, okay, or certain mimic certain behavior. Yeah, that we want. So I hope I am trying to clearly define which one is we talk about modeling in this class. Okay, our title of the class is transportation modeling, right? So we should start with this. Okay, so modeling is basically a simplified description of a system that assists the calculation and prediction. So it's very important. Okay, so uh, one of the book that I love, this is by Miller and Page, Adaptive Complex System. Yeah. So he said modeling is similar to sex, despite its importance, and most people do not want to discuss about it. No matter how much you read about it, it doesn't seem the same when you actually get around to doing it. Yeah. So, okay. Modeling required faith. Something different, I'm telling you. Okay. You see, what's the difference between science and religion? Okay. Both require faith. Just name it differently. Yeah. So faith is belief, expectation. Yeah. In science, we call it hypothesis. We call it axioms, postulate. Okay. Something that you need to accept by faith. Okay, they are the same thing. So what make it different is in science we use tests, objective tests. Okay? When one proof, okay, telling that our hypothesis or our axiom is actually incorrect, then we need to uh, disregard or reject our hypothesis. Okay. While this is totally different in the other side, see, in the religion and so on. So in science, you need to train to be honest and objective. This is the most important part of science, okay? Because all what you model, all what you say, okay, must be traceable, trackable, and repeatable. Meaning, when you publish, someone else can do it, okay, and get exactly the same result, okay, or at least between certain boundary of statistics, okay. So otherwise, it is not science, okay. So if you want to say this is science, it must be tested objectively. It should be repeatable, okay. So let's see, there are three views of model. So we can say in terms of concept, in terms of the form, or we go down into the quantified values. Okay, so when we said about the concepts, then you talk about the abstract view of the model. So you talk about the laws, the principles, yeah, the behavior. This is long lasting. Okay, so abstract model. Okay, and then from this concept, you bring down into a descriptive term. In this case, you talk about variables and relationship, the mathematical model itself. Okay, and then going down more detail, you put values to this form, yeah, to the variables and the relationships and the parameters, so that you can see the mathematics or the value of this. Yeah, and then you talk about the change in this kind of values in the variables. Okay, so all of these are still models. Okay, principles is also models. Okay, so I hope you can see the three views of the model here. So question is, why do we need to model? Okay, because the real world is actually very large and complex, isn't it? Okay, so if you want to evaluate, yeah, certain alternative course of action, then you need to try to experiment with the system, okay? And then you want to understand the system, okay? You want to experiment with that system, okay? To learn about that. Then to increase your own understanding, okay? To create a wise decision for your system, then you need to create model. Okay, so here it is. This diagram is actually summarize everything. Yeah. So you have the real world situation as an example. Okay? You have the road with the traffic congestion. Right. Okay. Then what you don't do is you do the real world solution there in the road. Why? Because that is the most costly. Okay, the most inefficient. Okay, because if you do directly here from real world situations, real world problem to real world solution, okay, then you experiment directly in the actual part of the road, then you experiment with the public, what the public will behave. Well, probably you can learn something over a certain time, but it's very costly. Okay, so that's why we need to model. Okay, so from the real world situation, you assume something, you abstract this, okay, you extract certain part of this real world that you are going to think this is very important, relevant for your problem. Okay, this is this abstraction or this extraction of the real world situation is called model. Okay, then you solve it in the model until you do experiment until you get the solution. Okay, once you get the solution, then you apply it to the real world. You optimize first, yeah, within the model. Then you apply it to the real world. Okay, this is the essence of model. This is much cheaper, and this is the advance of technology and science because we know how to model. Modeling is a tool, right, to optimize what we want to get. Okay, so now there are three levels of models. Okay, number one is description of phenomena. Okay, number two is to predict, and number three is to control or optimize. Okay, now question is, what is your level? Okay, say certain field of science. Okay, say probably in culture, anthropology, maybe in history. Yeah, well, I don't know. Yeah, they are not my field, but at the same time, okay, there are certain people who only know how to describe the phenomena. Okay, so maybe in urban planning, you know how to describe the phenomena. Oh, this traffic congestion happened because like this, like that. Okay, so you are in level one. Okay, but you are not able to predict, then you are still in level one. Okay, so when you graduate from level one, you can go to level two. What is that? Prediction. You should be able to predict. Using the model, you should be able to predict the future. Wow, I'm very proud. I can predict already. Okay, good. Okay, you graduate level two. Okay, but that's not enough. In our class, I want you to go to level three. What is that? to be able to control and optimize. Okay? Planning is basically control, optimization, optimization. So let's put it down into the actual form. Okay, so this is the abstract. Now go down to the form. So in the form, we have what is called function and variables, right? So say we have this kind of form, okay? Y is a function of x and alpha, okay? Alpha is the parameter, xi is the input, y here is the output. Okay, so basically we model there is an input, output, and process. Yeah. So simple. Okay. You have the input x, you have the output y, you have the process is a function. Okay. Within that process, you have alpha, which is the parameter. So when we say you describe the phenomena, okay, that means you understand the input, you understand the output, you understand the model, which is the function itself, and you understand the parameter. Okay? So from the past, you understand the current situation. Yeah, this is level 1. Okay? So learning about alpha is called calibration. Yeah. In the nowadays jargon of machine learning, okay, artificial intelligence, this is called learning, but actually this is, in the past we call it calibration. Yeah. So basically you just learn the parameter values. Yeah. Later when we discuss about regression model, you will understand more detail about this. Yeah, in the numbers. Yeah. So I'm talking about the form first. Okay. Next, you want to predict. You go to level 2, isn't it? You want to predict the future phenomena. So then you need to assume. Okay, the invariance. Remember, when you want to model, you need to understand the invariance. What is the invariance here? There are two invariants. Okay, two invariants that you need to see. Number one is the parameter alpha that you already learned in the first step must be invariant. Otherwise, you cannot predict. Number two, okay, the function, the model itself must be invariant, does not change. Otherwise, you cannot predict. So remember, yeah, when you want to predict, you need to understand what is the invariance. That is the assumption behind. Okay? So something that does not change, that is more important. Okay? So if you don't understand this, you don't understand modeling. The invariant is the most important. It's not the model. Because once you understand the invariant, you understand the assumption behind, you understand why it happened like that. Okay? So the model, simple. Yeah? You assume two invariants, the function itself, the model, and the parameter that you already calibrated does not change. Then you just input, you put the input, new input, not the old input, maybe the new input you put here, and then you will get the output. That's the meaning of prediction. Simple. Okay, so let's graduate second level, go to the third level, which is to control, to optimize. What is that? Okay, urban planning. When you said planning, that means you control. Okay, control means you have the goal, right? You have the target that you want. Okay, so that target is the output, the Y here. Can you see that? Yeah, you have the target that you want. Okay, and then what you want to get? The input. Okay, when you do planning, that basically you set that goal that you want. Okay, then you put into the model, you optimize to get the The input. What is the invariance here? The same. The invariance is the one that you learn in the first step. Yeah, this first step is very important, understanding phenomena. Okay, and you need to have the same function, but at this point, the function must be reversed, which is the inverse of that function. You see that? The invariance is important. Okay. Without that invariance, the function is still the same, the parameters still the same. You cannot control. You cannot predict. You got it? Okay. Okay. Anything to discuss? What did you learn from here? Okay. When you want to say, I want to describe the phenomena, remember, what is the input? What is the output? What is the actual parameter inside? What is the model or the function that you use? Okay, it doesn't really matter. Okay, next is when you want to predict. Okay, remember those are the invariant that you put in the. Sometimes you did not tell the invariance, yeah, but actually that's actually the most essential. Okay, which is the parameter inside and the model inside. Then simply you just put input, you get the output. That's prediction. Okay. When you say urban planning means you set the target. You want to get the input. Based on this input, okay, then you can get the planning, the control. You cannot control unless you know how to predict. Okay? Prediction is forecasting, isn't it? See, so it's difficult, okay? But you can do it, okay? So, yeah. So understanding the behavior, the phenomena, that's level 1. Okay. So in this part, you remember two things. Yeah? First is parsimony. Parsimony in the nowadays word is called stingy. Okay. So mean you simplify. Okay. You don't include everything. Say you deal with the model. Okay. You extract only something that relevant. Yeah. Exclude something that irrelevant. Okay. Modeling is always wrong. Okay, all models are wrong, not correct. Okay, but they are useful. Why they are wrong? Because they are not exact of reality. They are just simplified of the reality. Okay? So then you think about the perspective. What is actually important for this phenomena? Okay, what are the characteristics, what they do, what they do not affect? Okay, so you think about that in the first level. Okay, then you can go to the second level. So at this point, you extract the maximum relevant information from the history, from the past until the present, and then you learn about the future. Okay, you think about what kind of change, what kind of intervention you need to be done in the system. Okay, until you get the quantified level. Okay, the next one, now you want to control. That means you want to influence the behavior of the system. Okay, so well, some aspect cannot always be controlled. Okay, you can only control indirectly, yeah, or partially. For example, the weather can affect the farmer, but the farmer cannot control the weather, right? But you can make decision what to plant, okay? Or say, for example, you want to put cover and so on. That's possibility, yeah? So in this case, you investigate the robustness of the system based on sensitivity analysis, elasticity, and so on, okay? Next, let's discuss the model itself. Yeah, so model is just a specification of dynamic behavior of a system. Okay, so when we extract the system that being modeled, okay, so we say that this we abstract things from reality. Okay, we substitute the actual phenomena or the actual object into an object that we can manipulate. Okay, so in that case, modeling serves as a language, okay, that describing the system at certain level of abstraction. Remember this, okay? Model is a language, okay? So the purpose is to communicate in rigor, okay, in a precise way, okay? So these are example. This is take from the queuing book, so of course the example are more about queuing. Eh? So say when you get the system, for example, gas station or restaurant, this is very simple. Yeah. So you say you have a restaurant, okay? Think about the general entities is the customers, right? So and then you think about the special entities inside, or the table, servers, the kitchen, the cooks, and so on. So and then what are the entities that queue? Okay? Oh, the queuing of the customer for the table, okay? The table customer at the table waiting for the service, okay? And then and so on, okay? So the food is waiting to be served. Based on the server and so on. Okay, so any models you can start to extract the entities, yeah, the agent inside that. Okay, so now let's talk about the different type of models. Yeah? So model can be of any form and can serve many purposes. You know, the simplest uh, model is called physical or scale model. Okay. And then we can go into the second part, which is symbolic or abstract model, yeah? Including mental model. Yeah? When we say mental model is the model inside our mind, okay? Including the picture, the diagram, the chart, matrix table, and mathematical model. These are all our symbolic or abstract model, okay? So let's say you have a scale model, so something like this with 3D printer printing, so you can already create certain scale model. Yeah. So this is a three-dimensional physical object that look like the real one, except the size is actually smaller. Yeah. For example, the airplane, the building. Yeah. So they can try to check, okay, within the aerodynamic stability or within the earthquake, for example, if the building will collapse or not. Okay, so usually scale model is expensive to build, yeah, but with the 3D printer nowadays, we can easily create this kind of scale model. Okay, but the problem is usually the scale model does not lend itself to systematic optimization. Yeah, it's a little bit hard to use this as a mean for optimization, yeah, to control. Okay, then we go to what is called abstract or symbolic model. Okay, so mathematician use a mathematical simulation model, okay, which is also belong to abstract model. What is this? This is any set of rules. Yeah? Remember, any set of rules or relationship that describes something that is a model of that things. Okay, that include mental image within our mind. That include any books, any literary description, any rule of the game, any legal code. Okay, they are also abstract symbolic model. Okay, so the simplest that we are using daily is called a mental model. Okay, our mental model process using the concept which we manipulate inside our mind into new arrangement. Okay, we are what we think. Okay, inside our mind. Okay, but we believe this is correct, but actually this is not. Yeah, we think this is a fact, but actually this is the concept inside our mind. We perceive it as a fact. Okay, so well, when we are small, we probably play with our own imagination, right? So with the toy and so on. So the mental model is an abstraction based on our own experience, our own education, okay, depending on the purpose, the context that we have filtered, we have modified by each of us as individual, okay, based on our education, based on our culture, then we create our own mental model to represent the world around us. Okay, we are what we model. Okay, so our mental model are stable, oversimplified. Yeah, when something happen to contradict our mental model, what happen? We tend to dismiss, isn't it? Okay, so because we don't want to modify our mindset, our belief, our attitude. Yeah, sometimes we become prejudiced. Yeah, with our own opinion. Okay, when we deal with certain complexity, we tend to confuse. We tend to be dogmatic rather than empiric. Right? So yes, we need mental model to think. This is very fast. Okay, and our thinking depends on model. Okay. So the problem is our mental model are ill-defined, yeah, because we keep changing our own assumption. We keep changing our own purpose without we realizing it. Okay? The invariance is the assumption, but we don't clearly identify what is the invariance there. Okay? And you will say, you know what I mean? No, I don't. Because we are not easily communicate with others through mental model. So yes, individually we can manipulate it effectively, but in a group, it's very difficult to manipulate this effectively. Okay, so there we need tools. Okay, the one of the simplest tool is what we call pictorial model. So in this case, you have 2D dimensional photograph. Okay, the chart, the sketch of the systems, and so there you have improvement of mental model, isn't it? So this is an example of the map. So you want to create a road, for example, within this. Then you create a map and then you get the topographical map and then you draw on the map, isn't it? Okay. And then from there you can start to calculate. Okay. So the same thing with the diagram, isn't it? So you start to illustrate the interrelationship among the component. You know the input, you know the output, what is the flow or the sequence, the timing. Okay. So in this case, you start to use that diagrams. Okay. This is again tools, yeah, that improve against our mental model. Okay. And some diagram can be used for decision aid, for optimization. So example, network analysis and so on. Okay. And the table is also another tool that we use, matrix. Okay, so matrix represent relationship, okay, between components. Okay, then this can be used for optimization. And so when you deal with matrix or table, so this is you will always use this in this course. We will have a lot of matrices. Okay, so why we use mathematics? This is the most important part, yeah? Why do you use mathematics? Oh, I hate mathematics, you said. Well, you better love it. Why? Because mathematics is the most powerful, the most flexible, the most abstract language. Okay? More than 6,000 years of knowledge of human civilization has been embedded inside this language called mathematics. You don't need to create the mathematics. You just need to use it. Okay? all the giants before you already did it for you. Okay, you just need to use it. Okay, so this is the easiest model to manipulate. This is easiest model to analyze, to optimize. Okay, so it can be used to represent very widely variety of actual problems. Okay, so mathematical model consists of variables, okay, parameters, and function. Okay, so function will relate these variables with the parameters. As simple as that. Okay, well, it is very powerful, but because of its power can be abused or misled. Yeah, depending. This is tool, so yeah, it's like weapon, right? So it can be used depending on the objective, the perspective of the system being modeled. So you can lie with statistics, yeah, but very difficult to lie with mathematics. Yeah. So this is example of mathematics. Okay. So for example, profit is equal revenue minus cost. So in this case, logic, yeah, based on the definitional model. Yeah. Revenue is productivity times price. This is definition. Yeah. So the same thing with this one. Yeah. So population at times next year. So T plus 1 means next year. Equal to population this year, T, plus the birth this year and the death this year, T, and net migration. So again, this is definitional equation. Yeah, but sometimes you create what is called empirical uh, uh, equation. So say you use regression or statistical tool, then you input all the variable that you have, okay, and then the statistic will start to help you, and the tools, yeah, can help you to remove and include certain variable that you put. Then you will say, oh, this sales depends on GNP, price, and so on. So these are empirical based equation. Okay, so we can do that also. So this is basically called deductive model, yeah, based on the logic. This is called inductive model. That's based on the empiric, yeah, based on the data. Yeah. Both are valid. Okay. Don't say this is bad or the other one is good. Not necessarily. Yeah. Both are valid and good. Okay. So now, when you want to create model, okay, good modeling require reduction is simplification. Yeah. Again, yeah. So the success of the model tied with your ability to capture the actual behavior of the real world. Okay, you extract something that relevant to your purpose, to your context. Okay, so these are the steps that usually we use to create a model. So number one, you need to define what is your purpose, okay, your objective. So you identify the real world situation that you want to model, okay? This is very basic, so including not just urban planning, any kind, okay? So then you select the consistent view, yeah? Is it abstract? Okay, what kind of assumption that you put? Okay, okay, and then you start with the mathematical description, yeah, the variables, the function that you want, okay, and then you collect the data, you fit to calibrate the model with the real world, and then you validate, yeah. So you create prediction with that data that you have, okay, and then whether it is much. Okay, and then using this model, you can start to simulate, right? Oh, what if I do this? What if I do that? Okay, and then you interpret, yeah, this simulation result. You interpret in terms of the real world situation. Yeah, of course. Then when you implement, you check, yeah, whether your answer is actually reasonable or not. Yeah, if not, then go back, yeah, to the actual second step. Yeah. If yes, then you use the model further for prediction and the control of the real world. Okay. So Yeah, this one in the steps. Yeah. So you start with the project description. Okay. So you think about the concept of that. Okay. And then you start to create the actual uh, function, the variables, the parameters. This is the simulation model. And then you can put it into equation or run it in the computer. Okay. And check whether this is credible or not. Yeah. So if not, then you modify everything. Yeah, this is a loop, feedback loop. Yeah. So whether you achieve your goal or not. Yeah. If not, so again you look to modify this one until you get the conclusion. Okay. So modeling is a process. Yeah. It's not just one time from input to output and then done. No, it's a process of improvement. Yeah. Okay. Iterative improvement. So again, you check the current situation that you have, okay, and then you set a hypothesis, the axiom that you want to propose. Okay, this is my assumption. Probably will help the situation. And this is called hypothesis. And then you set up the mathematics on simulation model. So I gather the function, the variables, the parameters that you want. Yeah, and then you set minimum data to calibrate that model. Okay. And then again, you validate. Yeah. Later on, we talk about the validation. Yeah. And then you run this, okay, the current and test the hypothesis whether it's correct or not. Okay. And then compare this with the actual phenomena. Okay. Compare this with the result of this prediction and control with the actual phenomena. Okay. So model itself is just tool. Okay. You still need your logic. You still need your brain to validate all of this, yeah, or verify this in the real world. Okay. So what variable to include? The thing is, you need to control or to predict, right? So in that case, you need to include variables that you can control. Okay? I give you example. In the transportation, what you can control? You probably can control the demand through the price, probably. You probably can control whether we want to add certain links. Okay, so in that case, or you can control the, say, road widening or reduction. That mean the capacity you can control. You can control the speed limit, right? Things that you can control. You can control the, what else? Uh, adding link, remove the links. You can control the speed. Yeah, you can control the traffic signal. Yeah, the stochastic behavior of this traffic signal timing. You can control. Okay. Now, what you cannot control? You cannot control the actual flow. You cannot control the actual speed. You can control the maximum speed, but you cannot control the actual speed. Okay, you cannot control the actual density. Those are output, not input. Can you see? Something that you can control and something that you cannot control. So if you want to put both, you include, yeah. But the one that you can control, obviously you should put include inside your model. Say cost you can control, then include. Okay. But you said, oh, number of population. Well, you probably cannot control the number of population. Okay. Well, indirectly, yes, not directly. In that case, well, if you want to include that become output, not input. Can you get the idea or not? Time, you want to predict the time, then include that inside your model. If you want to deal with dynamic, then you include the time as a variable. So something that you want to include is something that you want to use. Okay? Something that you don't want to use, then don't include. So the number of birds on the street, you don't want to use that. The number of rat or the cockroach on the street that you want to build, you don't want to include that because they are not relevant to you. The number of trees probably you want to include. I don't know. Because that represents the cost. You got it? Okay. Which one you want to include is the one that you want to use. There's something that you include because you can predict, you can control. Okay. So important variables are the input, okay, the output, the external variables. The most important is the policy variables. Something that you can exercise your control, something that you exercise your decision. Those must be included. Is it clear or not? Okay. Those that outside external variables that you cannot control, well, you can include, you can, sometimes you don't include, that's fine. Okay. Or for me, I just put it in the cloud. So it will be affected in my model, but I just put there as external factor. Okay. Okay. External variables. Not that important compared to the actual thing that I can control. Clear, yeah? Without this understanding, then you will say, oh, I'll just include because someone else doing it. Well, no. You need to think what to include, what you want to use, what is your goal, isn't it? What policy are you going to do with that? What kind of decision? Then, of course, those policy variables must be there, isn't it? So you want to do a control using cost or time, probably. Yeah. But you don't include that. So how can you how can you do something with your model if you don't include? Right? It's not obvious. But there are things inside. Yeah? So this is called state variable, yeah? Internal variable. Within the model, there is internal variable within the system. Probably you cannot control directly. But you must put there because they are inside the system. So this is called state variable. In mechanical system, this is usually the position and velocity. Okay. The force is the policy. You can accelerate, you can brake, right? But the internal variable is the position and the velocity of the vehicles. Okay. These are in thermodynamics, we have temperature, pressure, and so on. So these are all internal state variable. When we say state variable, that means internal variable within the system. Sometimes you can control, sometimes you cannot control. It doesn't really matter, but that's inside the system. So you need to include that. Okay. So in dynamical system, when we say dynamical system, mean system with time. Okay. That system output here will depend on the input, system input here, the force, and then also depends on the past system input. So you see, when we talk about dynamic system, you see here, there is the same variable y here and the same variable there, y also. Can you see that or not? Okay. So in this case, you see the past will influence the future. Okay, so this is called state variables. This is the summary of all the past input. Okay, so well, other input variable, you can include the random variable to create some kind of probabilistic nature of the system, or maybe you want to do it deterministically. So only single value that estimate all the use. Sometimes if you put it into dynamic system, you have this kind of luck. See here, this is the luck. Y t minus k. Minus k is the luck. There is a shift in the time. So this is luck variables, luck output. So this is carrying information about the past. So how many steps behind? Okay. So here is the diagram telling the interaction among these variables. So you have input. Yeah, so you have input, set of input variables. Okay. There is a parameters. Okay. And internally you have certain behavior inside the model. Yeah. So and then this behavior will influence the state variable inside the model. Okay. And this is the function that will put all of this input and parameter and the behavior and the state variable into the output. And what you see is only the output and input, isn't it? The output is something that you observe, and then you compare this. Okay. So the one that inside you probably don't know. Okay. Well, using the model you can see, but the actual things how it behaves you don't know. Okay. So what you observe is only input and output. Is it clear? So this is what happened, okay, between two things. Yeah, we have the real world here on the top, and we have our own model on the bottom here. Yeah, and this is the time, current time t, and this is the future time t plus one. Okay, so the real world can be modeled as if there is a set of input here, the dot here, that uh, function into the next time, okay, using this f function. Yeah. Then when we said modeling, what we do is actually we extract certain information from this real world into a model. Okay. And we extract this function from the real world into our model. And then we predict the future, yeah, based on our limited formal model in order to predict the actual real world future. Can you see that? Hmm? Okay, so we have the real world, okay? We extract this into our model, okay? Actually, in the real world, there is a function, okay, to transform the current time situation into the future time situation. And then we extract that function of the real world into our model. It's a miniature of the actual function of the real world. Okay? This is what is called model. Okay. So in real situation, okay, uh, this is what happened in the one level of the world, one panel. Okay, and then there is also possibility in the lower model here. Okay, we have a new emerging behavior because of different agent, okay, different entities influence what is actually happening in the real world. So this is much more complicated than what we model. Okay, so when we talk about complex adaptive system, okay, we are not just modeling input or output over time, but we need to think in terms of agent. Okay, that means individually everyone will have different kind of model. Then we need to map all of this, yeah, into a simulation that we can start to see the emerging behavior of the actual macroscopic phenomena based on the microscopic phenomena. Okay. Okay. So to give you example, okay, so I will show example. Let's go to the class model. Can you see this model? Okay, and then go here. Here, this is the example of microscopic traffic animation. So I make this. Not perfect, but this is just a show an example. So here I model every individual. Yeah. So there. Yeah. This is every individual of the vehicles we model. Yeah. So this you can change. Yeah. You can play here. Every individual of the vehicles will have different force. You can change the forces. You can change the perception of each individual here. Okay, and you can also change the road, yeah, and the vehicles. Okay, so how you generate the vehicles also. So, for example, I want to behave from left to right and so on. So you're supposed to get there. You start from right, yeah, different uh, behavior coming here. Okay, so this is what I'm talking about, modeling each individual agent. Okay, so you start to see the time and space, yeah, of each individual agent. So one of the uh, simplest model is actually just dynamical system, so based on time, or network graph, it is based on space. Yeah. Sometimes we can create what is called cellular automata. Last week we discussed about it for the uh, uh, urban growth model, remember? And that is time and space. Okay. But when you talk about multi-agent system, MIS, so you have the time and space and agent. So that means each agent can learn, can adapt. Yeah, there is connectivity between agents, so in the network, and there is some kind of interaction between network, yeah, between the agents. So you can model anything with this. Yeah, I think in the near future this will become the more trend. Yeah, especially with the AI. Yeah, AI itself is an agent, isn't it? So when we say about multi-agent, that means you will have many agents, not just one. Okay. Say one of the simplest model is static model. Yeah. So this is used in disease modeling. Yeah. So this is called SIR. Yeah, susceptible infected recovery. So this is used usually in medicine. Uh, so the susceptible, the number of people susceptible to certain disease, yeah, depending on the number of infected, and this is the number of population N. Yeah, the same thing, the number of infected depends on the susceptible and the number of population N, and the number of people who recover from that disease depending on the number of infected. So this is a very simple differential equation. Yeah. No geography, no friendship connection, no time, only the flow. Yeah. So, but using this simple model, you can already connect, yeah, each person in a macroscopic level. Once you put this into agent base, then you go much deeper, yeah, into microscopic level that will have the what is called uh, emerging behavior, yeah, self-organized behavior in the macro level. Yeah, the whole economic is also emerging behavior. Yeah, when the flow of money or the flow of people in the traffic is emerging behavior of the micro level. Each individual of the vehicles, yeah, or the people there, yeah, is a micro level. Okay, the flow, yeah, is actually emerging behavior at the macro level. Okay, the same in the traffic model. Okay, in the micro level is each vehicle as an agent moving. Okay, and the macro level you will see the dynamic flow. Okay, so when we talk about later on fundamental diagrams, flow equals speed time density, this is static model, yeah. But that come from a complex system model with this multi-agent. Yeah. So when we talk about modeling, okay, we talk about usefulness. Okay. When we said, oh, can you validate this? In 1990s, I talked to Jay Forrester, yeah, the father of system dynamic, yeah, about the model validity. And he said, model validity is actually relative. No? So the usefulness of mathematical simulation model should be judged in comparison with our mental model, okay, or other abstract model that will be used. Yeah. So think about whether the clarity of the structure that we model is there. Think about whether the underlying assumption is mentioned. Okay, whether there is a time varying consequences is there. Then you will see this model is probably funny. Okay, so yeah, this is what J. Forrester said. Yeah, by constructing quote, yeah, by constructing a formal model, our mental image of the system is clearly exposed. Right? General statement about the size, the magnitude, the influence are given numerical values. Okay. As soon as the model is so precisely stated, one usually asks, how he knows that the model is right? Then become the controversy. The controversy often develop over whether or not it is the reality presented in the model. Yeah. Some question miss the first purpose of model, which is to be clear, clarity, and to provide concrete statement that can be easily communicated. So model is a language. Okay. So we can never prove that any model is an exact representation of reality. In fact, it is not. Yeah. So models are not to be judged by absolute scale that condemn them for failure to be perfect, but on the relative scale that approve them if they succeed in clarifying our own knowledge, our own insight into the system. Okay? So model is just a presentation of the reality. It's not the reality itself. Okay? So when a model is reduced to diagram, to equation, and so on, then when you start to talk about the underlying assumption, okay, the invariance, when you can communicate with others, okay, when you can compute the time patterns to determine the actual behavior implied by the model, then you can reasonably hope that you understand the reality better. That is model usefulness. Okay? So what is the purpose of data? Oh, I want to collect data. I don't have data yet. Well, data will not solve your problem. Okay? The purpose of data is only to validate and calibrate your model. Okay? Do not find the model, do not find the data to solve your problem. Okay? So, what is calibration? What is validation? Calibration is the process to determine the value parameter. Remember the function, okay, a while ago. Okay, so the y is a function, right? This is the output of the input, yeah, and the parameter alpha, yeah. So calibration, okay, when you see calibration, is to determine the value of the parameter alpha. Okay, how to determine that? You need to know the input, x. You need to know the output, okay? And you need to decide your function. So three of them, then you can get the parameter. That's the meaning of model calibration. Okay. So then what is model validation? Okay. So validation is a process to test the fitness of your calibrated model using different data from the data that you use for calibration. Okay. So one technique is called uh, K-fold validation. Yeah. So what happened is you have the whole data set here. Okay. And then you divide into K. For example, you divide into 5. Okay. So then what you will do is you include only 4 to calibrate. Yeah, to calibrate this one. Yeah, input. This model consists of the input. Yeah, this is the input and the output, right? So I will put like this. Yeah. So you only include 4 of them to calibrate, and then you use one part of that to validate. Yeah. So remember, it's a process to test the fitness of your calibrated model using different data from the data that you use for calibration. So this is your whole data set. Okay. So you use only some part of that, okay, to calibrate, and then certain part that you don't use to validate. Okay. And then you take run. Yeah. So the second part, say you have A, B, C, D, E. Yeah. So you use A for validation. Yeah. B, C, D, E for calibration. And then the next round, we do this, the next one. Yeah. So B for validation, A, C, D, E for calibration, and so on. Yeah. At the end, you will get the whole data set for calibration and validation. Yeah. That's called K-fold validation. Okay. So in validation, you ask whether we build the right product or not, yeah, the right model. The next part is model verification. Okay. So you're concerned with ensuring, okay, whether the feature that you have is actually happening in the real world. Okay. So check whether it's what you model is actually indeed present in the real world. So this is interpretation of the actual world, of the actual model into the real world. So you're asking, are we building the product right or not? Okay, up to here. Is there any question to discuss? Go ahead. Yeah, go.
Sir, since we also have a research that we have to do, is it correct that we're aiming for the optimization type of research?
Correct.
Okay.
In your group project, you need to do that, right? So you're heading toward optimization. Yeah. Uh, at this point, we still discuss the big picture. Okay. And then later on, we go into the real modeling. Okay. And then you develop the scenario, then you develop the policy, and then you optimize. Okay. You find a scenario that actually the optimum. Okay. And you calibrate the model. Okay. And finally, of course, you verify. You validate and you verify. So all these steps, yeah, the same that we talked today, okay, will be used again and again. And so I'm still in the general discussion here. I did not even talk about which model. Okay. Anything else to discuss? You understand the concept, right? So there's no. Okay. I hope you understand the meaning of description phenomena, prediction, control, calibration, validation, and verification. Those are the things that I want you to understand. Yeah. Okay. Okay. Let's continue in that case. So next is simulation. What is simulation? Yeah. So once you have the model, yeah, and you have the equation to describe how the system changed, then the change are accumulated step by steps to show the behavior or the pattern of the system. This is called simulation. Yeah. The step-by-step numerical solution of the actual model. That's called simulation. Okay. So simulation is a mathematical model that describes the behavior of the system over time. So sometimes you said, oh, simulation is just software product. Yeah, okay. So not just a mathematical formula. Yeah. So using simulation, you talk about what if. Yeah. You learn by doing it. Yeah. You learn about the system. Yeah. You build the model and make it run, and then you ask, oh, what if I do this? What if I do that? Yeah. That's the most important part of the simulation, isn't it? So what if? So you do a role play. Okay. What if I reduce? Okay. What if I increase? Or what if I add this one? Huh? What if I limit certain things? So, okay, is there any way to make it a cheaper way? So you start to optimize using simulation. Yeah, this is just uh like a child doing a role play with a toy. Yeah. So with this, you start to understand the reality, you start to understand the complexity of the actual model. Okay. So yeah, these are just famous simulation quote. Yeah. So run it again. Yeah. Okay. So uh, any simulation, any model, okay, some sense is always cartoon of the reality. Yeah. Don't think your model is reality. Yeah. Because reality is very complex. Yeah. This is just a small part. It's a cartoon that captures certain essence of situation. Yeah. That we hope it captures the essence that we want to model in the real world. Okay. So the purpose is to gain the insight, yeah, into the actual system, how it works. Okay. And then what kind of policy that I can change the system. Okay. And then you test your hypothesis, isn't it? You have certain concept that you want to check whether this is true or not. You want to, you have certain policy, you want to have certain change. Yeah, policy means change, right? So you have certain change that you want to improve the system. This is your hypothesis. Then you test, yeah, using this kind of simulation, yeah, using the model. Okay. Then why we need to do a simulation? Because you don't really disturb the actual system. When you experiment in the actual road, you actually disturb the actual system. Okay. But when you do it in the simulation, yeah, you can change whatever you want. One example that I often use is actually swapping the number of lanes. Yeah, within the road network. Okay, say I want to keep the number of capacity constant. Okay, so then I need to swap the number of lanes in order to make it better. Okay, if you do this in the real world, that's very costly. Yeah, say I want to reduce in this road, and then I want to add that reduction to another road, swapping the number of lanes in different network. This is impossible to do it in the real world, yeah, because it's very costly. Yeah, but in the simulation you can do it. You don't need to disturb the actual system. Yeah. So uh, the reason to use simulation, yeah, one thing is to demonstrate, yeah, the actual internal process of the real simulation. Okay, and sometimes we we don't use mathematics, yeah, because the mathematics is too complex and you cannot solve it mathematically. Then you go to simulation. Okay, there are certain mathematics that you can solve. There are certain mathematics you cannot solve. Then you use simulation. Yeah. So simulation always solves, but only certain pattern that you have, only certain trajectory. Okay. So you run again, you have different trajectory. Okay. So, but using mathematics, you can solve it in general way. Okay. In simulation, you only solve it in certain pattern, certain trajectory. Yeah. That is the if you can solve it with mathematics, solve it with mathematics because that is better, because that is general. Yeah. If you cannot, then use simulation. That's you can always create the trajectory of that solution using simulation. Yeah. So when you experiment the policy on the real system that is too costly, too dangerous, yeah, then you use simulation. Yeah. So certain things that too long to yeah to do it in the real world. For example, the city growth. Okay, it compress 100 years. You can compress it in a few seconds or a few hours. Yeah. So that is part of reason why you use simulation. Right. So, but if you can find the analytical solution, the mathematical solution, okay, then you use the mathematical solution. That's the best way. Okay. So, because if you can solve using mathematics, you can get the form of the solution. That form of the solution will tell you the general response without any numerical simulation. Okay. So then again, yeah. So if you can solve it using mathematics, solve it using mathematics. So if you don't, then you use simulation. Okay. So uh, if you cannot solve it using mathematics, you solve it using uh, simulation. For example, a non-linear complex system. Okay. Then for such system, only simulation can do it. Okay? Because we can do the numerical simulation. Okay. So simulation will not give you general solution. Will only will not tell you the all possible behavior. Yeah. Simulation will only give you one-time history or trajectory of that system that you run. Okay. Because you set a certain condition, certain condition. But mathematics is better. If you can do mathematics, do it mathematically. Okay. So this is the reason not to use simulation. When you use mathematics, that this is simpler, then don't use simulation. Okay. When you develop the model and it's too costly, too time consuming compared to actual decision, and maybe your decision is simple enough, you don't need to model, isn't it? Or when your computer running time is too expensive for our today's computer, then you don't need to use simulation or mathematics in this case. Okay. So not everything can be solved. Okay. And when there is a probabilistic pattern in the system that is susceptible to sampling error, okay, while the analytical drive is not, then you use the analytical solution, not the simulation. Okay. So simulation probably requires certain training. Yeah? So this class is also one of the training. Yeah? You can use this. Sometimes it can be very costly to train, and certain software, for example, a transport system, say you want to buy fishing is $10,000, right? So that's many years ago. One student in India crying, I cannot buy those kind of software because our salary is not enough. Okay, so can you develop it? Yes, I will try to develop it. That's why I develop IFN transport, you see, to help people who doesn't have actually the actual money. So I give it for free. I hope you can use it. Yeah. Well, it's the same value in terms of simulation, in terms of the output. Okay, the difference is the visualization. Okay, you can get the values, numbers, okay, the flow, okay, you can check because this is the actually open source, so you can check the actual software inside the code. Okay, so but you can even modify. So it's practically I put it in public, so it's your own. Okay, but at the same time, the visualization is not there. The animation, the visualization that make looks good is not there. That's a lot of work to be done. So if you want to contribute, that's fine. If not, it's fine. So that part is probably still lacking. Okay. So now caution. Yeah. So you use software. Yeah. So when you use software, one thing you need to remember is Kigo. What is that? Garbage in, garbage out. Okay? So even you buy very expensive software, okay, your input is garbage, then the output is garbage. Okay. Kiko, garbage in, garbage out. Say the model required OD matrix, example. Yeah? Right? The classical traditional transport model required OD matrix. Okay? But you don't have automatics. In fact, automatics to get the automatic is very expensive. Okay, in the history of Metro Manila, you have only two. Yeah? In '96 and 2016, isn't it? Those two projects that create the automatics. Very, very expensive. So then practically you don't have uh, accurate result based on that inaccurate data. Okay, so be careful when you use the model. Okay, so even if you have the data and you have the model itself cannot solve the problem. You solve the problem, not the model. Model is just tool. Okay, the mathematical relationship is not the solution. Okay, you need to develop the scenario, isn't it? Okay, always check the unit, the dimension in the model. Okay, so even if after you run all of this mathematics simulation, even if look good, yeah, if the solution does not make sense, then come back to the assumption, the invariant that you set, okay? Whether it is true or not, isn't it? So you reconsider, yeah, what is the invariance inside, okay? So, so certain model cannot solve easy answer to a very complex problem, okay? This is what I often see. Yeah? The students usually getting so involved with certain model. Say you use linear regression, okay, and they think that this model is the truth. Okay, this is very funny, but often happen, isn't it? Because you so involved with your own model, with the solution that you think, yeah, you forget that this is actually a model, not the actual system that you analyze. Yeah. So remember, good model and solution represent good approximation, okay, of the actual system, but this is not the solution of the actual system. Yeah, this is just a tool. Yeah. Okay. Without this, often happen because you engross, yeah, yourself very focused, right? And you believe this is true, but this is not. Okay, so in the beginning, I'm telling you this, so that you will not get misconception. Yeah. So there is a misconception also that a larger model, more complex model, will be more sophisticated model is better. Well, that's not true. In fact, the reverse is true. Yeah, this is called Occam razor. Yeah. Uh, uh, this is the principle that you need to remember when you do modeling. Yeah. This is William Ockham, is a Franciscan monk in 13th centuries. Okay. He said probability should not be posited without necessity. This is in Latin. Yeah. So the meaning is you prefer a simplest hypothesis that's consistent with the data. Okay. So if you have two theories, okay, explain the fact equally well, then you prefer the simpler theory, not the complex one. Okay. So a short hypothesis is the fit with the data is unlikely to be coincident by luck. Okay? A long hypothesis that fit the data, it's more likely to be just coincident by luck happening. Okay, so I will give you example in mathematics. Okay, there is a theorem you can search in Wikipedia. This is called Weierstrass approximation. Okay. So Weierstrass approximation theorem states that any continuous function within a closed bounded interval can be uniformly approximated on that interval by just merely polynomial. Polynomial function, that's one of the simplest function, to any degrees of accuracy. Yeah. So the problem here is overfitting. I'll give you example here. So I have a few dots. Yeah, this is the x is the input, fx is the output. Okay, so this is the few dots of data. Okay, so what happened is let's uh, run this. So this is the first model. Okay, linear, and then this is the second model. Okay, non-linear, blue. Okay, and this is the third model. Oh, the third model you see here is much fit with the data. It's passing through all the data. Okay? And then the fourth model is the green one. Again, it fit with the data, passing through all the data. Okay? And question, which one is better? Which one is actually the blue one, the red one, the black one, or the green one? Huh? What do you think?
I think the blue one, sir.
The blue one. Why? Why? Why the blue one?
It shows there's variance that's
Hmm.
accounted here.
Yes,
Also, it's simple. While the first one, the black one, doesn't really. It's a variance that uh,
correct. Yeah. So the blue one is the simplest model that close to the data. Okay, not exact, close to the data. Yeah. While the black one is a linear model, is the simplest model, but this is not that close. Yeah. We are not sure whether this is outlier or not, this one. Okay. But if this is true data, then this is the closest nonlinear model that we have. Yeah. But when you start to put matching with the red one here, this is overfitting already. What's the meaning of overfitting? The meaning is this model, the red one or the green one here, overfitting, okay, it matches with the data that you have. Okay, it calibrated but not validated. Okay, meaning you can only match with the actual data that you have, but you cannot predict. Once you cannot predict, you cannot control. You can only understand the phenomena. You are in level one. Okay, but you cannot predict because prediction means different data. isn't it? Okay, so I hope this is clear enough. Yeah. Okay. Yes, John, Kenneth, you want to ask question? Go.
Yeah, sir. Hi. Is there a risk that making a model too simple might hide important dynamics? Like, how do
Hmm.
we know when we've simplified too much?
Yeah. What's important is actually, again, yeah, what is the reality that you want to represent within your model? Okay. And whether the input you can use to predict, to control your model. Okay. Whether the assumption is all clearly stated, whether the structure of the model is clear, okay, whether you can understand the actual reality based on this model. Those are the uh, criteria that I repeat again and again in this slide, isn't it? Okay. So there is no clear cut to tell this is too simplified or this is too complicated and so on. So okay. Modeling itself is an art, isn't it? Okay. Within the science, there is an art. Okay. So as much as possible, we want to get the best model that we want. Okay. Whether we can achieve our goal through this model. Okay. If you cannot, then maybe too minimum. Okay. Your model, you need to improve because you cannot achieve what you want. Right. So actually, that is very good question, yeah, John. Yeah. Again, this is an art within the science. Hmm? Any other question or discussion, probably? Yeah. You catch the actual problems in modeling. Yeah. So let's go to the next slide. Okay. It is, wait, I will discharge this one. Hmm. Okay, so there is, this is fundamental. Okay. There are certain, uh, this is the model. Yeah, we discussed this on Finish. So there are certain website that discuss about the next topic. Yeah, this is the one that we discussed. Next topic, the traditional transport planning. So you can open this. Okay, so let me put it up so that you can see. Okay, and this will discuss about regression mostly, and these other tutorials, yeah, that you can also check. Yeah. So all discussion is based on this tutorial. Yeah. This is whether this is linear or non-linear. Okay. It's there. Okay. Let's start with that. Yeah. Okay. Are you ready? You downloaded already the slide. Okay. So this is the beginning of what we call traditional urban transportation planning process. Yeah. So let's discuss first about forecasting and planning, yeah, and urban transport planning process. Okay, and one of the simplest model is load factor. Yeah. And then we discuss about regression. Yeah, so I will start with simple linear regression and then go to nonlinear and multiple linear regression. We'll go using matrix. So we can use. Excel, yeah, for this one. Okay, so first, when we talk about forecasting and planning, right? You are in urban planning, yes, sir. So both forecasting and planning is about predicting the future, isn't it? Okay, both based on historical data. Okay, both have certain assumptions, certain invariance. Yeah. So the difference is forecasting is actually passive, objective. Yeah. We predict what will happen in the future, but you have no intervention. Okay. So example, you predict the population growth, yeah, or economic growth. Yeah. So you have no intervention what to do about it. Okay. So in that case, you just forecast, okay, about the future. But when we say planning, okay, planning means active and subjective. Yeah. So what's the meaning? Yes, you forecast about the future, but you guide what will happen in the future, based on certain intervention, certain policy level, yeah, to control that path to achieve your objective. So you have, so planning basically is a control, is an optimization on itself. Okay? So planning is a process to examine the potential future action, okay? And then you guide the system toward the direction that you want. Yeah, so this is the definition of urban transport planning, the process to prepare the physical facilities, the road, the services, yeah, for all mode in transport and in the future. Yeah. So it is a proactive. Yeah. So, and you check the need in the future, okay, and then you have certain goal. What are the goal? To provide the safe, rapid, comfortable, yeah, convenient, economical, probably environmentally friendly, yeah, efficient access and mobility for all, yeah, equity, yeah, good for people and good, yeah, uh, to satisfy human needs. Yeah, these are the goal. Yeah. So you need to have certain intervention, important here. Okay? So when we talk about transfer planning, okay, that's very multidiscipline. Yeah. So it will include social science, economic, planning and architecture, system engineering, maybe part of civil engineering, and you have certain mathematics, statistics, and physical science. Yeah. Say about the soil mechanics, about the pavement design. So these are very broad. Yeah. So when we talk about traffic engineering, we are in here. Yeah. But when we say transport planning, is very broad. Yeah. Well, that's not include the soil mechanics. Yeah. So transportation engineering itself is very broad field. Yeah. All of this. So when we said about UTP, urban transport planning, yeah, these are the process. Okay. So you have the organizational inventory. Okay. You have certain policies and technical. Okay. You have certain citizen participation here. Yeah, you collect the data, economic data, population data. You collect land use, okay, transportation system data, the road network itself. Maybe you have certain data of travel. So terminal regulation, yeah, traffic control, and the financial and certain values of the community, right? And then from here you create the analysis. Yeah? So our class is only very limited, only in the analysis, yeah? Not include the everything else. Yeah? So maybe under in GIS class you will talk about the surveillance and mapping and so on, yeah, in here. Okay, so you have certain plans, certain policy that you want to include. Okay, and then you develop the model. So our class is only in the modeling. Okay, so these are the usually the model. Yeah, you model the land use, you model the trip generation. Okay, trip distribution. Yeah, how they select the mode. And model split is how they select the mode, and then you apply this into the road network in order to you assign these trips into the road network to get the flow. Okay, then from all this data, okay, that you have, this is called socioeconomic data. Combined with this model, you create the future. Yeah, again, you develop the same model. Uh, remember, there is invariance. Yeah, the invariance are the parameters and the models. Yeah, the functions. Uh, in transport, we use the same model. Yeah? This is called four-step models. Okay, for the future, and then you evaluate all of this. Yeah, whether this is correct or not. Okay, so our focus is actually here. Yeah, it is called FSM, yeah, four-step model. Yeah, trip gen, trip distribution, model split, and traffic assignment. Okay, so this is called classical demand forecasting model. So you start with the decision to travel, yeah, for each individual. So we discuss about person trips, and not vehicle trip, person trips or good trips, okay, for the goods. So trip gen, you talk about from where to where they travel daily basis, yeah. So how they decide what is the purpose of their travel. Okay, so in here you have what is called trip production and trip attraction. That means production means the home, okay, residential area, and attraction is the destination outside of the home. So that's can be the workplace, can be the school, can be mall, can be any office. Okay, so and then once you know, yeah, based on that trip purpose, you know how many is the production of each zone, okay, and what is the attraction of each zone. Yeah, so the whole maps of the world you divide into zone. Okay, so then you start to create trip distribution. Yeah, from where to where. Yeah, so this is what is called OD matrix, yeah, origin destination matrix. So again, origin destination matrix is in the unit of person trips or good trips, yeah, not vehicles. Okay, person trips. Okay, so you calibrate using the OD data. Okay, then the third step is called mode choice or model split or model choice. So now each of this person trip need to use vehicles, right? So maybe pedestrian, they use their own feet. Okay, what kind of mode are they going to use to travel? Okay, so remember, yeah, the first one is just the trip purpose from where, yeah, okay, and then or going to where. Here is connecting this dot, yeah, from where to where. So trip distribution is not just the production and attraction, but connecting the dot, okay, based on certain costs and certain time, usually. Yeah. Again, that model split is again based on all variables that you have, okay, to tell which mode do you use. Yeah. The last one is called traffic assignment or network assignment. So once you know which vehicles, okay, and you combine them into one unit, yeah, using a conversion factor of PCU values. Yeah, for example, bus is like 3 times of car and so on. Okay, then you put them into, you assign them into network. Then you can get a flow. Yeah, this is the traffic assignment. So these are the 4 steps model. Okay. So, okay. Remember, yeah, in the first 3 steps, okay, this is person trips. Okay. Okay. And then the third step is actually to convert from the person's trip into vehicle trips. Yeah. And the last one is the one that create the flow. Yeah. Later on, when we discuss about IFN, okay, ideal flow network and so on, this is mostly about the fourth part. Yeah, this is called ideal traffic assignment. So only to choose the road part. Yeah. Okay. So the purpose of transport demand model is to predict the future volume, yeah, of traffic on its road, okay, from origin to destination by certain user group for certain trip purpose using certain mode, yeah, at certain route at certain year. See, so this is time and space and agent. Can you see that? Yeah. So there is time, okay, there is a space, yeah, and certain agent. Yeah. Okay. So let's go deeper with certain simple forecasting. Yeah. So you can have 2 approaches. Yeah. One is called based on transport demand. The other one is based on transport supply. Yeah. So transport demand means the flow, the movement of the people, of the goods. Okay. Transport supply means depends on the location, the capacity, the condition of the transport facility that you have, depends on the road network. Okay. So the traditional 4-step model tend to be in transport demand. Okay. The IFN or the ITA, the indirect transport traffic assignment is based on transport supply. Okay, so you start with the regional population, socioeconomic data, and land use, and so on. So you project this one. Okay, and then you have certain zone if you want, based on certain allocation that you have, and then you calibrate that using certain model that you use. Okay, and then you think about certain alternative, yeah, that you have a scenario to improve this. Yeah. Based on that, you check the resulting in the target year. Okay. Okay. And check whether what is the level of usage and what is the benefit and what is the cost. Okay. And then you compare, yeah, the alternative that you have to select the project or scenario that you want to propose. Okay. These are the simplified process. So, yeah, one of the simplest way to forecast is called growth factor. Yeah, this is very useful but very crude. Okay, so P can be the price of population. Okay, so when we set the subscript T here, that means today or current year. Okay, when we put T minus 1, that means yesterday or last year. Okay, when we put T plus 1 here, that means tomorrow or next year. Okay, so when we define these 3 values, okay, then we can calculate what is called growth factor. Okay, so say population of today minus population last year divided by population last year. So this ratio, yeah, of change divided by the the state represent growth factor. So in economic, this is called return. Yeah. So basically just growth factor. Okay. So with this, you can predict. Okay. Remember, to predict what you will do, you set the invariance. Okay. When you want to forecast, you always have certain assumption. Yeah. So this is the formula I just copied a while ago. Okay. So then you assume this is one of the assumption that you set. So the forecast means the growth is the same. So when you set the growth is the same, okay, then you can forecast. Yeah, just simple. This is equal. Then you can put it into forecasting formula, isn't it? So tomorrow, okay, equal to today, multiplied by 1 plus the growth factor. Yeah. So you want to practice this? Maybe a few minutes. Okay, so can you do this in Excel? Yeah. So you just type and if you finish, so you share your screen, okay, as your recitation. So you have the slide. I will just close the sharing here so that any of you can start sharing here. I will put, uh, in that case, I need to put you in the co-host. Yeah. Anyone want to share your screen? You can. Mm. So everyone is co-host. Yes. Okay. Go ahead if you want to show your work. Yes. Beltran. Yeah, Romeo.
I sir, can we go back to the given, sir?
Okay. This one.
Thank you, sir.
Okay. So Ken, you want to share your screen? Yeah. Yes. So how much?
Yes. Can everybody see my screen po?
Yes. Yes. You can see your screen. So
Yeah. So basically, I first computed for R,
yes.
which is this formula.
Yeah.
The population difference in population between 2023 and 2024 divided by the population of 2023. And then I use the formula to compute for X, basically multiplying uh, the 2024 population plus times the sum of 1 plus R.
Yes.
So the forecasted population for 2025 is 5.8556 million.
Very good. Yeah. So this is one of the simplest. Yeah. Thank you. Who else want to show? Okay. So yeah, very good. So you can don't forget to claim your recitation at the end of the class. Okay. Every time, every class. Okay. Good. I hope this is clear enough. So very simple model of prediction, right? Okay. Now, yeah, this is if you want to use, the answer is there in the slide anyway. Yeah. So I put the formulas there also, so you can practice. Yeah. So remember earlier I discussed the three, right? So level of modeling application. So you understand the phenomena, prediction, and optimization. Yeah. So I hope this is clear enough. Yeah. So we will do this using the second model, which is called regression. Okay. What is regression? Yeah. In the language of machine learning, AI, this is called supervised learning. Supervised learning. Yeah. So you have the input and the output. Yeah. So the input is called independent variables. Yeah. The output is called dependent variable. Yeah, because that depends on the input. Yeah. So regression is a modeling technique of numerical data. Yeah, that relate a dependent output. Yeah, or response. Yeah, variable y here, and one or more independent variables. Yeah, input. Yeah, this is the variables input can be any type. Okay. In regression, the input can be any type, can be categorical, can be numerical. But, okay, but the dependent of the output must be numerical. Oh, how about if my output is not numerical, it's categorical label? Then it is still supervised learning, but this is not regression. Yeah. So I give you example. Let me find the example here. Say you go to, can you see the website here? Okay, you go to a free online tutorial, you go to Ideal Phone Networks. Okay. Here, you go to this one, table classification. Yeah, this is still supervised learning, similar to regression, okay? But this is based on categorical. So this is an example. Say this is many example here you can use. Okay. So I will just open this. So one of the example is transform mode. Yeah. This is for mode choice or model split. So you have the data of any, yeah, can be numerical, can be categorical, but on the dependent variable or the output must be categorical. Yeah? In this case, bus, train, or car label. Okay, this is not regression. This is called classification. Yeah, classification. Yeah, regression and classification both are called supervised learning. Yeah? Because you have the input and output as your data. Okay. So with this, you can train. So you just click this one. There, I got the training. In this case, accuracy is 100%. And these are the model. Yeah, I'm using ideal flow network as a model here. Okay. And then based on that, you can predict. Yeah. So this is your input. So I create a random test here. Okay. And based on this random value, you can predict here. So when you predict the output, which is the class, right? So I create a new random data and I predict. So this is the class is trained with certain confidence level. Can you see this? Okay. And well, because this is ideal flow network, so it can actually generate. Yeah, it can generate not just can predict, it can control. Okay, so you can actually get the, oh, if I want to get the bus, what is the input? Yeah, yeah. If I want to get the people who use car, what are the possible input? Okay, so you just click here, you can get the, which this one is randomly generated, not necessarily the same as the input that you have. Okay, so this is one of the model, yeah, supervised learning model. Yeah, this is also called machine learning. Okay? Now come back to this slide. Okay, let's come back to the regression. Okay, so when we said regression, okay, the dependent, not label, not categorical, must be numerical, must be numbers. Okay, that's the difference between regression and classification. Is it clear or not? Okay, so any model, you can think of that as a system. Okay, so system usually have input and output. Yeah, so let's call the system E dot, that means dot is the input. Yeah, and Y is the output of that X input. Yeah, so system receive the input X and produce output Y. So the system itself, we call it E. Yeah. Okay. And what is called linear? Yeah. So linear system, linear regression. Okay? That means a system called linear system if a system satisfies two conditions. Okay? If you want to say this is linear or not, you check these two conditions. If these two conditions satisfied, then it is a linear. Okay. Otherwise, it is not linear. Yeah, non-linear. Okay. So, linear system, when your input are added, yeah, you add two input, then the output, yeah, when the system receive the sum of two input, it will also produce output equal to the sum of the two input. Yeah? So here I can separate them. I can decompose them, and then I can just add. So this is one of the condition of linear system. The second condition is multiplication, constant multiplication. If I multiply that with certain value A, yeah, the input, if I multiply with certain value, okay, then the output is the constant of this can be put it out. Can you see this? Okay, the constant can be put it out from this. Yeah. So the system that receives a constant multiplication of the input will also produce the output equal to the constant multiplication of that input. So these are the two conditions to say that, oh, I'm using linear model. Okay. So if I combine these two conditions, okay, we will have what is called linear combination. Okay. So we summarize these two conditions into one. Okay. That means I multiply and I add. Okay. So in this case, become linear combination. So the linear system is a system that produces output equal to the linear combination of the input. That's exactly the same as earlier. Okay. So when you put this into graph, you will get a straight line. Yeah. Okay. In the static system. Yeah. In dynamic system, not necessarily like that. Okay. So when we said linear regression, be careful. Okay. we say linear regression is linear regression in parameters, not necessarily in variables. So, example, here, okay, polynomial regression, something like this. Okay, the variable have square, okay, or exponent p, clearly nonlinear. Okay, but this is still called linear regression because the parameters are still linear. Okay, the same thing with this kind of what you call as nonlinear model. Okay, so can you practice this? Okay, is this linear or which one is linear, which one is non-linear? Anyone? Well, the first one here, you probably say this is linear. That's clear, right? This one, yeah. So the question is, if you can transform any of this into linear model, then they are linear. Okay. In fact, all of these are linear model. Okay. Even if look like non-linear, or maybe people call non-linear model, yeah, even in my website, but they can be transformed into linear. So they are still linear regression. Yeah. Understand? Okay. All of these are linear because I can transform all of this into linear model. Yeah. Any question? Someone raise the hand? No. So, okay. Yeah, later we will discuss how you transform, yeah, using a non-linear model. So let's start with the simplest one, yeah. This is called simple linear regression. So only one input and one output with two parameters, yeah. Can be one or two parameters, yeah. So it's a linear relationship between independent variable and dependent variable. And the graph is straight line like this, okay. And this is how you interpret the error. Yeah? So the error is always vertical like this. Yeah, this is not the only way to define the error. Yeah, there are many ways. Yeah, I can define error perpendicular like this, right? Yeah, so I can define the error perpendicular. Yeah, like that. So this is another way. Yeah, but usually we use error as the difference between this value and the predicted value. Yeah, the data and the predicted value. So let's compute a simple linear regression using the same data earlier that you just typed a while ago in growth model. And maybe I just use different numbers of the year. Yeah. How do you do that? So we have 5 data points, right? We have 5 data points, and we want to predict the next point. Okay, so then the question is, first you need to do is plot, yeah, this data. This is the first step. If you want to do modeling, try to plot this, yeah. So this is an example of the plot, right, of that data. Oh, it seems to be a straight line. That should be a linear model, right? Okay, okay. But when we said linear model, okay, oh, there are many possible linear model. Come on. Right. Yeah, can be the blue one, can be the red one, can be the green one. Yeah, everyone have their own opinion, right? Or which line is the best in this case? Anyone, any opinion? Okay, as you said, the red one is like the green one, the other one said the blue one. How about you? What do you like? Huh? Oh, it is the best because I said so. Well, that's not objective enough, yeah. Uh, make the reason why you choose that line. Okay, okay. Okay. The blue one is the best. Okay, or the red one. What do you think? Yes, red. Why, Dennis? Why red? Yeah, you can claim that. Why red?
Sorry, just my opinion. Because they all touch the red line touches all the points.
Oh, really? Is it because that's the point? Okay. Uh, what is the best model? Depends on the criteria, isn't it? Best is always depends on criteria. Okay. You said the best because that's the point. Okay. So he said, oh no, the blue line, that's the first point of the data. So that's his criteria. Okay. And then the green one is in the middle of all points. So that her criteria, isn't it? And the red one passed through most point of the data. In fact, it doesn't touch that point. Eh? There is still error. So then we need to have more objective criteria, isn't it? Okay. One of the objective criteria is, of course, to measure the error. Yeah. So again, even error, definition of error can be different, you know. So one of the error that often used is discrepancy and the difference between the prediction and the real data. Yeah. So that means this one, this error, yeah, in the vertical one. Yeah. So error is positive, yeah, when the data point is above the line, and error is negative when the line is above the data. Okay. So then there's a problem. What is the problem? When you sum all of this error, it becomes zero. Okay. So, well, that's exactly the problem. Because some is positive, some is negative. Okay, the sum is become zero. Yeah. It's a problem because the sum of all error just becomes zero. It doesn't work. Okay. So then, okay, to make it work, we don't use sum of error. We use sum of square error. Yeah. So the baseline should minimize the sum square of error, not the error itself. Huh? Because if you sum of the error, becomes zero. So by doing this, yeah, this is actually you assume something behind the scene. You assume something. What's the assumption there? Yeah, you assume that the error is normally distributed with zero mean and constant variance. Okay, so if your actual data does not match this, yeah, then you probably don't use that model. Maybe you use other model. Okay, remember the assumption is important. The invariant is the important part there. Okay, let's calculate that. Huh? So this is your data. Yeah, I calculate the blue line, the red one, and the green line. Yeah, based on that criteria of some square of error. Yes, the red one. Yeah, Dennis, you're right. Huh? The red one apa nih by luck ya. Your guess is by luck ya. This based on minimum sum square of error or SSE. Okay. So So based on that, we can actually derive. Yeah. So if you know this is minimizing SSE, so you can derive the formula. Yeah. These are the formula that you can derive. Yeah. I will not go to the derivation of this formula. You can refer to the statistic book usually. Yeah, you'll give this. Or in my website, I derive. Okay. Check the derivation there. Okay. This is the derivation to get the two parameter, yeah, slope and the intercept. Okay, so how do you use this? This sigma means the sum. Okay, so what's the meaning of this? This means n is the number of data. Okay, x y meaning you multiply the x and y, the input and output first, and then you sum. Okay, this one you sum all of the x. This one you sum all of the y. This is you square first and then you sum. In here you sum first and then you square. Can you see the difference? Okay, so I will show you. If you want, you can practice, but maybe you don't have time in the class. You practice after, yeah, at the class. Okay, so here I'll just give you the solution here. So say you have the input x and the output y. Yeah, the input is the year, the output is the population. So what you will do is multiply, yeah, x and y. Yeah, you get this value, right? And then you square it. You see? So you square the x. Okay. So 1980, so square become this value. Okay. And once you get these two values, okay, then what you will do is you input, yeah. You sum all of that. This is the sum. The one in red here is the sum. So you get n is 5 data, right? So, and then x, y is here. This is the value. Okay, 3, right? And then sum of x, this is the sum of x, 9950. And then sum of y, this is the 17.2. Okay. And then you square first. This is the square first, and then you sum. So you get this value, 9198, something, something. Okay. And then this one is you sum first and then you square. I this one. So this is 9950. Okay, and then you square. Okay, so when you input all of this, you get the value. Yeah, this is the slope. Once you have the slope, you just get the average, the mean. So the mean is this value. So then you can get the intercept. Is it clear or not? Yeah, you need to practice if you don't see this. Yeah. Once you have the slope and intercept, okay, then you predict. Yeah. So you predict based on the same input x, and you have the slope. Then you predict. Once you have the prediction, then you minus, yeah, that prediction with the data here. Yeah. This is the prediction with the cap, and then you minus. Then you get the error, and then you square that error. Yeah. One more things. Each of this data you minus with the mean also. Yeah. Each of this data 2.1 you minus with the mean, and then you square. Yeah. That is called square mean difference. Yeah. You will use this value later. Yeah. For calculating the R squared, yeah, coefficient of determination. Okay. So this is the model, simple. Yeah, population is equal to the slope multiplied by the year, and then plus with the intercept. Yeah. In this case, the intercept is negative, right? Then once you have the model, what you will do? This is calibration. Yeah, calibration is to get the parameter. Yeah, the two parameter is slope and intercept, isn't it? So understanding phenomena. Okay. The second step is prediction. Yeah, prediction means you have the input, you have already the model, so you use the invariance. The model is the same, and then the parameter is the same. Okay, so all you need to do is just change the input. In this case, the change is the year. Okay? Then you get the output. So you predict. Is it the same as growth model a while ago? Not the same. Yeah, this is probably better. Yeah. Why? Because this include all the years, yeah, historical data. While the growth factor include only one last value, isn't it? So regression is much better than the growth factor. Okay. If you predict only use growth factor, you practically you get only straight line, flat straight, not even straight line in the slope. Yeah, here you get a better. Is it clear? Question about this? Yeah, so you need to guess what model you use. Yeah, modeling is an art and science, because your model is not necessarily linear, isn't it? So uh, how do you know? You check the scatter plot. Yeah, you also check the residual. Okay. So and then there are certain scientific way to examine the goodness of fit. Okay. So you check the R square, the F value, the T value. Okay. Now, so this is the simple linear regression formula. So you have this uh, parameter and intercept. Okay. Yeah, this is the derivation. Yeah, how we get that formula. So I will just skip this part. Yeah. So you can actually use this is called ordinary least square OLS. Yeah? So setting the first derivative and set it equal to 0, then you can get the any model, yeah, based on least square. Yeah, and you can practice if you want. This one simple. You want? And then you share your screen. This is only 4 data points. Oh, Romeo, you want to say something?
Yes, sir. We just need to plot best fit line, sir.
Yeah. You can just plot the best fit line in Excel. You can also do that. Okay.
Can
So,
I?
oh, sure. You share your screen. Yeah.
Can you see my screen now, sir?
Okay. I'll guide you. Yeah. This is the oh, wait. Don't close it yet. Can you show again? Uh, hello? Romeo, can you show it again? Oh, it disappeared. Okay, maybe his internet is in problem. Anyone get the answer? Yeah, Justin, you want to?
Can I try, sir?
You try again. Yeah.
Uh, Wait.
Yes.
I'm sorry, sir. My laptop went low, but
Okay. Hmm.
For a while, sir, I'm trying to figure out how to share my screen.
Oh, at the bottom you have share.
Uh, Actually, sir, I used my scientific calculator.
Oh,
Can I
okay.
screenshot it and
Oh,
try
sure, sure,
to?
sure.
I'll just try to screenshot it, sir,
Okay, okay.
and send it to and
That's it.
try it, sir.
Yes,
Okay.
yes.
For a while, sir.
Yes. Anyone else want to? Romeo, you want to show your screen again? I will help you in that. Okay. So, can you click that dot there in the screen? There. Yes. So, can you click the dot in the screen and then right? Yes. And then you here. No, no, no. Wait. Come back to that earlier. To the regression part of that one. Click the dot. Right click. Right, set trend line. There, add trend line. Slowly. Add trend line, yes. And then you check the display equation on chart and display R square there. No, no, why? On the right side that you have, okay, you click one of these dot on your chart. There, add trend line. Slowly, slowly. Add trend line, yes. There at the bottom there. Can you see on the right? No, 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 don't set equal to 0. Yeah, that display equation and then R square. Yes, there you have it. Okay, so you have the equation and the and the R square. Okay, so you can also do here in the sheets. Say you go to E2, for example. Okay, and yeah, you click there in the yeah in the E2, and then you can type yeah, equal slope of the y, comma, and then the x. Yeah, there is a function already in Excel that you can use directly. Yeah. This is also work for a logarithm, polynomial, power, and exponential. That's the non-linear part of that. Yeah. Okay. Yeah, I hope this is helpful. So there is a function called slope and intercept. Yeah. So you can also use that. Okay. And go again to your data. Oh, wait. Show in your data analysis, data tab. Okay. Oh, you don't have data analysis. Okay, go to the file. Okay, and then option there. And there is an add-ins there. Add-ins. Can you see add-ins here? There, you click that. Okay. And go here in the go at the bottom here. Can you see the go? Yes. No, 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 no. Just go. There is oh, what is this? Uh, sorry, I cannot read. So you click this one, maybe data analysis, the first one, maybe. Why this is in Russian or Ukrainian language? So if you click OK, if not, maybe some of them. So if you click OK here, you're supposed to see a data analysis part in here. Is that correct? No, no, unfortunately, no. Yeah, there is an add-ins called data analysis. Okay? If you want to use that, you can also use, then you can get the regression more yeah, if you have right one, you're supposed to have a new menu here. Yeah, maybe different add-ins. I cannot read that Russian. Okay, anyway, so maybe different add-ins. Maybe the other two. This one maybe. No. Maybe you check all so that you can see. Maybe, yeah. There you have data analysis there. Okay. So when you click this, you have regression. There. Go there. Okay. Using this is easier. Yeah. You can set the Y range and the X range. Okay. So you just click these values. Okay. And then you click this value here. This one. Can you see my screen? My arrow? Yes. So you select the input, the Y, and the X. Yes, you click that. There, you select the input. Oh, this is Y. The Y is the other one. And, yes, and then click back. Okay, and then the X range again. You input there. Okay, and wait, don't click yes. Here you put the residual, standardized residual plot, and normal distribution plot, and so on. So these are the plots that you can put here. The normal also, and line fit plot. Okay, and then click OK. Yes. So based on this, you will see when you click OK, there. Okay, this is the result. Yeah, so you can see whether they are normal distributed or not, right? Okay, this is the residual plot. Yeah, if you have more data, you can see they are supposed to be in the plan. Yeah. Okay, and this is the value. There's a lot of values, but this is the one important thing. Yeah, you need to check the R square. Okay, adjusted R square. So your R square is bad, and you need to check the coefficient. What happened? Why this is not the same as your result a while ago? Okay, and you need to check the coefficient, standard error, t statistics, and the f value. Yeah, this is your value is bad. I don't know how do you uh, select the input and output, or maybe your image is not working well because this is supposed to be the same as the output of the as in the plot a while ago. The result is not the same. So maybe something is wrong with your way. In the sheet one a while ago, can you see? In your sheet one, right? So here, you're supposed to get the plot with this slope is 2.4 and intercept supposed to be 9.2, but your result is not the same. So this is probably incorrect. Yeah. Okay, so please practice again later on. Yeah.
Copy, sir. Thank you.
Yeah, thank you. So I hope the others also can use the same technique. Yeah. Let me
Can I
put.
now stop sharing, sir?
Yes. I will share my screen. Mm. 22. This is the result if you calculate, right? So question is how good is your regression, right? So here are the most important. There are so many numbers that a while ago if you use Excel. Okay, the most important that you probably want to see is the string. Yeah? The R square, F, standard error, yeah, and T statistic. Yeah? So the R square represent the whole model. Okay. Usually this is just rule of thumb. Yeah, if the R square is larger than 0.8, that's mean good model. Yeah, if your R square is very low, that's probably you have certain uh, uh, nonlinear model, or maybe you need to use different model. Yeah? And then for the T statistic for each model, okay, for each individual parameters, including the slope and intercepts, okay, you check, yeah, the absolute value must be larger than 1.95 and then 6. This is based on the normal distribution, yeah, of 5%. Okay. So if they are low in T value, yeah, less than that, that means that variable must be close. Okay. Okay. So you compare overall fitness, yeah, compare several models. Which one is the best in terms of R square, in terms of F, yeah, or SSE? And then for the variables, you use t-test. Is it clear? Yeah. For the model, you use the R square probably, and for the variable that you use t-test. Okay. If the value of t value is small, that means it's a weak variable. You probably want to remove because they happen to be there by chance. Okay. This is how you do. Okay. So R square is just based on 1 minus SSE divided by SST. Yeah. So SSE you already calculate, that is depending on the actual observation and the predicted value, you minus and then square. So this is sum square of error. Yeah. This is sum square of total, I mean the total variation. That's come from only the Y value and the average of the Y value. This is the based on the output only. And then you square, yeah. Yeah, you minus and then you square and then you sum. So this is not depends on this is depend on data, not depends on the prediction. Okay, so when you put the ratio and minus this ratio, you get the R square. Okay, or this is called coefficient of determination. Okay, so a while ago, this is what I asked you to do, right? So this one is the value that you will calculate. From there, you can calculate the R square. Yeah. Because R square is just 1 minus this SSE here, and then divide by this SST here. Can you see? Okay. With that, you get a very good R square in this example here. So, but if you have many variables, yeah, if you have only one variable, R square is good. Yeah? But if you have many variables, you don't use R square, you use adjusted R square. That in that screen of Romeo a while ago, yeah, using the regression, you will get also adjusted R square. Yeah? So adjusted R square means depending on the number of coefficient, yeah, and the number of data. Yeah. So the R square is now depending on the mean of square error and mean of some square total. Yeah, not just SST and SSE, but now have parameters. Okay. This is for multiple linear regression. Yeah? If you have more than one input variable, okay, then you use this. Is it clear? Okay. Rule of thumb, again, R square or adjusted R square should be higher than 0.8, yeah, 80% of the data, yeah. So if how about if 0.6? Maybe okay, more moderate, depends on your decision. And if your model is very scattered, probably you will still accept that. But if your model is R square is less than 0.5, you probably want to use other model. Yeah, very poor. Can R square become negative? Yes, it is possible, but it's called square, but negative. Yes, that means your error is so big compared to your data. Yeah, that is a possibility. Yeah. So another way to compute the overall model is using standard error. Yeah, this is the MSE or square root. Yeah, we already put this in the adjusted R square anyway. So another way to do is using app statistic. Yeah, so this is based on the statistic and the degree of freedoms. Okay, if you use Excel, it will come out with this value. Yeah, this table is always there. Okay, so all you need to do is to check this F value. Yeah, comparing with this degree of freedoms. Okay, and then you will check whether they are valid or not. Yeah. You check the significant level, error degree. If less than 0.5, then it is fit. Yeah. If otherwise, it is not fit. So next, yeah, this is ANOVA table, analysis of variance. Yeah. Next is a T statistic. Yeah. T statistic is useful to check its parameter, yeah, its coefficient in the model. Yeah. This is basically the slope divided by the standard error of that slope. Yeah, this intercept divided by standard error of that intercept. Yeah, this is basically strength of its variable or the intercept itself. So you check the absolute value of the T statistic. Yeah, if this is less than 0.96, that means no good. Yeah, if larger than this, that is good. Okay, so I summarize. Okay, so you check these three, yeah, R square, the F, and the T statistic. Yeah. Well, if you are saying, oh, between say 1.7, what happened? Yeah, it's okay, but that error is big. This is the error value, yeah, for the absolute value of the T statistic. So here is the example result of the Excel linear regression. These are the point that you need to consider. So many numbers, don't look at all the numbers. Focus on the one that is important, isn't it? So R square or adjusted R square, yeah, this is must be bigger than 0.8, and then this significant F must be smaller than 0.05. And then this T statistics, yeah, this is the one that must be larger than, say, 1.65 or 1.96. Okay, simple. Okay, and then after that, of course, the coefficient. Yeah, so here the slope and the intercept that you would use to predict, right? So yeah, all these are just performance index, but this is the one that you will use. Is it clear or not? Yeah. So the coefficient is the one that you will use. Yeah. So once you have that, so you can use many different way. Yeah. Again, there is a Excel function for that. Yeah. So you use slope and intercept function. There is also data analysis. I asked Romeo to do that a while ago. Yeah. So you can do this also in add-ins. Yeah. And here are the steps. So you first plot the scatter plot. Okay, check. Yeah, we did the scatter plot. You will see if straight line, that's linear model. If not straight line, probably non-linear. Okay, and then you guess. Yeah, what model? Okay, so if it is possible, you transform. Yeah, if it is non-linear, you transform into linear, and then you compute. Yeah, the model parameter. And then you compute the statistical fitness, yeah, the R square, the F, the T, and so on. Okay. And then if it is nonlinear, you need to come back to the nonlinear, and then you interpret the model. Okay. So when you use scatter plot a while ago and you right click there, you will get this trend line, a trend line, yeah. And then you can select, isn't it? You can select linear or non-linear model that already exists in Excel. Okay, I will teach you how to create your own non-linear model transformation. Yeah, not exist in Excel, but you can also do it. Okay, so again, you can just if you use Excel, you can just use this check, yeah, display equation and display R square. Yeah, and then just be careful. Yeah, if you use polynomial, you may have overfitting. Yeah, uh, I don't recommend to use polynomial unless you use it not for prediction, just for um, you know, matching only. Yeah, polynomial model is or moving average model and polynomial model usually very sensitive. Yeah, you can match all, but not good result. Overfitting for prediction. Okay, now let's discuss the transformation of nonlinear model into linear. Okay, so you have this kind of value, yeah, function. Okay, then you can uh, make it linear. One way is you plot, okay, and then you change the scale of the plot. Yeah, this is one way to do. Yeah, you change it to logarithm. Yeah, you can do that in the right click and then scale of the x, scale of the y. Okay, so if you use log, yeah, log, this only should be log. Yeah, uh, if it is linear or not, yeah, then you can get the result of transformation. Yeah. Or you can change the scale. For example, if this is y is one divided by, this is a reciprocal model. It is not in Excel, right? Not automatic. So in that case, you transform into 1 over y. Yeah. So you will get a linear model. Yeah. So if after you transform, yeah, this coordinate, you get a linear model, then this is linear model indeed. Okay. So to transform algebraically, you need to understand two rules, yeah, power rule and logarithm rule. Yeah, so this is the power rule, okay, and this is the logarithmic rule. Okay, so based on this, we can transform. Yeah, so some simple nonlinear model you can transform into linear. Okay, so here are the transformation. Okay, so I will demonstrate this next week. I think now it's already 9 o'clock in your case. Okay, I will demonstrate this next week, how you will transform this and then practice. Yeah. So in the meantime, so please read this slide and then especially the last part with the matrix, you will have a problematic if you don't read and practice at home, isn't it? Okay. So please try to do it first and read first, yeah, and practice first before the class. Is that okay? So it, because we have not reached this part, so the assignment there I will postpone. Okay, I will postpone. Not the deadline is not next week, but maybe when we finish the class. Okay. Thank you very much for today, and let's meet again next week for the non-linear transformation. Yeah. Okay. I want to remind you one thing. For the group project, can you input just the name and then the tentative project that you want to do in the entry in Moodle? Yeah. Only one person in the group is enough. to submit. Yeah, I already set it into group. Okay. Okay, thank you very much. So see you next week.
Thank you, sir. Bye-bye.
Yes.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Study this, yeah, power rule and logarithm rule. I remember you do it you when you are still high school, but probably you forgot. So please check again.
Can
Okay.
do, sir.
Thank you, sir.
Yes. Okay. This recording.